Good evening, everyone. Assalamu alaikum. So before to start, I want to let you know that I'm coming from Morocco, and we are a francophone country, so my English is a little weak. So please apologize. I excuse if I will make any mistakes. So I'm going to talk today about the management of inter-domain quality of service, starting by presenting a general context of our study and defining management of quality and service in IP networks in general, then introducing our mechanism, which named QoS-CMS mechanism, and presenting a study of performance of our mechanism, and an extension to include our mechanism in BGP protocol. And finally, conclusion and some perspective. So as you all know, internet is in permanent evolution due to the huge diversity of traffic circulating on internet, and also the burst of the volume of traffic due to the mobile devices who are in permanent increase. So ISP have an important challenge to ensure end-to-end quality of service for traffic who crosses multiple domains. So as a start, quality of service can be defined as the capability of network to provide better services to selected network traffic, and it can be described by parameters such as bandwidth, packet delay, jitter, and packet loss rate. As we can see in the figure, we have multiple type of traffics, and each type needs have his own requirements in terms of quality of service, and the network and service provider, internet service providers, must respond to all these QoS requirements. So to respond to these requirements, several models have been introduced at first concerning the intra-domain management of quality of service, starting by the in-serve model and the diff-serve model, MPLS traffic engineering, and also the combination of MPLS and diff-serve. All these models ensures quality of service, but only in intra-domain, since they define the quality parameters in the service limit agreement, and it's based on definition of class of service. This definition is done by the network administrators, so they are specific and valid only in the initial domains, and the traffic that crosses multiple domains don't have the needed quality of service from the end to end. That's why several research work have proposed models to ensure end-to-end quality of service, but until today, there is no standard implemented in internet to ensure end-to-end quality of service in inter-domain networks. So that's in this context, we propose our new mechanism named QoS-CMS. Our mechanism allows to ensure quality of service in inter-domain environment by implementing in each domain a server named class manager that will be able to exchange all QoS information between neighboring domains. The architecture of our mechanism is based on introducing in each domain or autonomous system a server named class manager that will collect all information concerning quality of service in domain and exchange it with the neighboring domain. So the step one of our mechanism is the intra-domain classification. Each domain or each autonomous system have to employ her own quality of service policy using one of the multiple models that ensure quality of service in intra-domain, like in-serve or diff-serve or even MPLS. So then the router of each domain send all information about the different classes of servers that they had created to the same server of their domains. Next, each CM server define a class a class table that contains the ICE number attributed to this class of service, the class number, the bind weight attributed to the class of service, the level of priority to the class of service, the Q limit, which means the maximum packet number that class can include, and also indicates if they apply the random detect algorithm for the scheduling management. Then, since each class manager establishes his own class table, the neighboring class managers exchange their tables. And this way, by establishing a TCP session between the two servers and sending a group of messages, starting by the identification message that indicate the IP address and the AS number of the class manager. Then they exchange the content of their class table by sending a set of announcement messages that contains the parameter of each class of service defined in the domain. Then, if there are a modification or update concerning one class of service, an update message is exchanged between the CM servers. The fourth step, when the CM server receives the CT table of his neighboring CM server, he sends it to his own routers, and this way, all routers in the neighboring domain can take into account the quality of service, the class of service defined in the neighboring domain. And if a packet arrives to the neighboring domain, he's gonna find a class of service that have the same parameters of quality of service defined as in its initial domain. So, to take into consideration security too, so we propose to run AAA authentication between the communication between router and the class manager server, and to establish a secure channel between the router and the CM server to secure the communication. Then we have to secure also the communication between the class manager. So we propose to use a AAA authentication server that allow a secure channel between the class managers. So our mechanism presents several advantages. First, it allows a continuity of quality of service for traffic that crosses multiple domains. And it has a reduced hardware cost because we need just to implement one server in each domain. It's a secured mechanism that we take into account the security. And also, it's not need of important overhead, since the establishment of class of table and the exchange can be done just not several times, because the definition of class of service happens just in the start of the configuration. So to evaluate the performance of our mechanism, we have run several simulations. We have run two scenarios. The first scenario represents the networks, the ordinary networks without implementing our mechanism, with multiple sources of three different types of traffics: voice, FTP, and data. And the second case, in the second scenario, we implement our mechanism, which means the class manager. And we measure and compare the variation of loss ratio and delay between the two scenarios by evaluating the QoS parameter and especially the CR in several studies, and measure the improvement ratio in each case and for each type of traffic. So some of our results show that the implementation of our mechanism, which is presented by this curve, improve significantly the loss ratio for the voice case in this case, and also it improves the delay. As an extension for our mechanism, we propose to introduce our mechanism in BGP protocol to promote the choice of a path through an IS with which we have established the QoS-CMS agreement, and automatically choose, while taking the routing decision, choose the path that ensure the quality of service and to use it for routing traffics. This can be done by defining a new attributes in the BGP paths named QoS agreements that indicates if at least one of autonomous system for those contained in the IS path parameter of BGP established in the inter-domain IS QoS agreement with the current IS. The size of this sorry. The size of the new attribute is 1 byte. It's 0 if no agreement is established, and is 1 if an agreement is established. We define also how we can handle errors concerning this new parameter. If the parameter is syntactically incorrect, the notification message error stub code should indicate invalid QoS agreement attribute, and the data field of this notification message indicate the type, the length, and the value of the invalid attribute. And we define also a new subcode that indicates invalid QoS agreement attribute in the error subcode of message updated number 12. And we have to modify the breaking tie algorithm of BGP by including a new step in the algorithm as the third criteria that indicates we must eliminate routes that have QoS agreement equal to 0, so which means prefer routes that cross a domain with which you have a QoS agreement to routes that are not. So as conclusion, we have proposed a new mechanism to ensure quality of service offered in the inter-domain traffic, which is flexible and simple and coherent, and also have the ability to be extendable. The performance studies results showed the interest and significant improvement ensured by our mechanism. And as a perspective, we want to implement and study the impact of the new attribute that we use and that we propose to include in the BGP protocol, and also we are searching in the SDN field where we are done some research concerning the proposing a new model of management of quality of service in multi-control SDN environment. So thank you, and questions.
Any questions for Sara?
Yeah.
Have you tried to implement it and see how it works?
Sorry, I don't understand.
Can you repeat the question, please?
Have you tried to implement or model this, or maybe or later propose it as standard or something like?
Okay, we have tried to done a test bed and requirement, and that show that our mechanism improves also the delay and the loss ratio. But it was a small test bed. We don't have the necessary material to run the complicated architecture or topology.
And maybe propose it as kind of internet standards?
Okay. What? Sorry.
Are they trying to make kind of internet standard based on their research?
No, there is no standards until today. Just multiple research works, but no standard as is implemented in internet today.
Well, I mean, not just scientific research, but proposed as a standard.
Yeah. We're trying to develop an RFC to propose this mechanism, but we are still working on that.
Any other questions? All right. Thank you, Sara.